Hello and welcome back. In example 4, we have a right circular cylinder that's inscribed in a cone with height h and base radius r, and we're asked to find the largest possible volume of such a cylinder. Now we can draw a 3D version of this, so we'll sketch a 3D version. Here's the cone, and if we draw a cylinder inside of that cone, if it's inscribed, it might look something like this. That would be a circular cylinder that's inscribed in the cone. Notice how the edges are right along the edge of the cone, or the sides of the cone, and down on the bottom here, it's flush up against the bottom of the cone. So here's a right circular cylinder that's inscribed in a cone with height h, it says, and base radius r. But let's take this and put it in a two-dimensional setting. I mean, there's a lot of symmetry in the 3D. You know, if you take a cross section at any different angle, it's always going to be the same. The cross section going straight on will be the same as the cross section if you go sideways. So we can think about this in 2D. We can think about just the shadow of these 3D images in a 2D setting. That's going to be easier to deal with. So in 2D, the cone looks like a triangle. Now the radius we were told was r. So this is the distance from the center out to the edge of the cone on the bottom. Center out to the edge in the bottom. That's r. And then the height of the cone is h. So the cone, we're just looking straight on at the cone. It can be coming out of the plane, but we don't have to consider that aspect of it. Now the cylinder, if you look at the shadow of the cylinder, it's going to look like a rectangle in 2D. Now this point here on the rectangle, we're going to call x comma y. That's going to be like a control point where if we move this point along this side of the triangle, that's going to create a cylinder for every single point that we're at. As soon as we specify that point x comma y, we'll be able to create very skinny cylinders that are very tall, and if we move it down here, we'll be able to create short cylinders that are very wide. So there are all kinds of cylinders you can inscribe inside of that cone. Let's draw one where the control point is down here. That's going to lead to a very short but very wide cylinder. So then our goal is to find the largest possible volume of such a cylinder. So our goal is the volume function. That's what we want. We want the volume function of a cylinder. Now the volume of a cylinder is going to be pi times the radius squared times the height. The radius of this cylinder is given by just x. That's this horizontal distance, which is given by x. It depends on what x is. If your point is up here and your x is small, then you have a smaller radius. If your point is down here and your x is very big, then you're going to have a bigger radius. So the radius is not actually r. R is the radius of the cone. We're interested in the radius of the cylinder because we want the volume of the cylinder. So we have pi times the radius of the cylinder squared. Oops. Radius we said was x. And then times the height, but the height of the cylinder, let me erase that. The height of the cylinder is given by y. So there's the volume of the cylinder in terms of two variables. Now what we need is an equation that relates these two variables, x and y. Well, notice that x and y is trapped on this line here. If we can get an equation for this line, we'll get a relationship between x and y. Well, thankfully we can get an equation. We have a point on that line, r comma 0. We actually have another point, 0, comma h, if we wanted to use that, but I'll just stick with r, comma 0 for right now. And we have the slope of the line, because if we travel from this point up here down to this point right here, we're going to have negative h in the y direction and positive r in the x direction. So the slope is negative h over r. We'll call that m. So then we get the equation y minus 0 equals negative h over r times x minus r. So we get y equals negative h over r, x. And then if you distribute the negative h over r to this other r, the r's cancel and you get plus h. So after we replace y with negative h over r x plus h, all we're going to have is volume in terms of x. We'll take a moment to clean that up a little bit by distributing in the x. And oh, we did the third step. Didn't even notice it. The third step again was to take any two variable function and reduce it down to a single variable. Now you may go directly to the single variable function, and that's fine. But a lot of times if you break things up, you're going to end up with a two variable function, which then you can bring down to a one variable function using some kind of constraint. Like this point x comma y is on this line. That's a constraint. Or the volume of the can is 1,000 cubic centimeters. That would be a constraint that you can set up an equation for. Now we can move on to our fourth step, which is take the derivative with respect to x. So we'll get negative 3 pi h over r x squared plus 2 pi h x. Okay, we can factor this out. Pi hx, there's a common pi hx in each of these. We'll have negative 3 over r x. And then we have plus 2. There. Let's figure out where that is equal to 0 and maybe doesn't exist. Well, it's going to be 0 when x equals 0 for one thing. And then when negative 3 over rx plus 2 equals 0, so that's negative 3 over rx plus, oops, equals negative 2. So x equals, let's see, the negatives cancel, and then you multiply by the reciprocal. So we have 2r over 3. Okay. One of these, I say, is nonsense. Which one is that? If you said x equals 0, then that's correct. X equals 0, you're not going to have a cylinder anymore. So this is nonsense. These variables mean something in this problem. So x equals 0 is meaningless. Now the D&E case, there aren't any x values that make this does not exist. Remember that the only thing that's on the bottom of the fraction is r, but that's a constant. That's the radius of the cone, not the cylinder. So then we can take the only x value that we have and plug it into the volume function, because we're asked to find the largest possible volume. Find the largest possible volume, not just the dimensions, but the largest possible volume of the cylinder. So to get the volume of the cylinder, we can use the volume function that we created. And we have a couple of choices about which one to use. I'll go ahead and choose that first one that's already factored. That looks like a nice one to plug into. Pi times x squared times quantity negative h over r, 2r over 3, so that's x, and then plus h. So we get 4 pi r squared over 9 times, ooh, the r's cancel. So we get negative 2/3 h plus h, which will be 1/3 h. Or you can just write h over 3. And now we've got 4 pi r squared h over 27. Let me make that look like a 7. And there we have it. That's the largest possible volume of a right circular cylinder that can be inscribed in a cone with base radius r and height h. Thanks for watching this video, and see you next time.